correlations between concept.
So let's resume.
Thanks. Okay, I'm just gonna pick up where I left off. So, okay, so what we'd been looking at, right, was we're looking at this rank 1 matrix estimation problem. We have a model like this. We observe a data matrix A. We'd like to recover our signal V. And so what we looked at is using an AMP algorithm to do this, right? And so the AMP algorithm takes the following form. It's our standard AMP, but we've replaced, the W with our data matrix A. And so what we motivated by kind of looking at the distribution of, at least the first iterate was that, what we'll find is a state evolution like the following. And with the state evolution, we get our main theoretical results. So the theory is similar to what we have for the original or the standard AMP. So under similar assumptions, which are, assumptions on regularity conditions about my function ft, sort of assumptions on the empirical distribution converging of like the signal and my initialization, we get the following result, right? So for some pseudo Lipschitz function that now has 2 inputs, which my signal, this is the true signal, right? And my matrix iterates, then we get that the limit of this sort of pseudo Lipschitz loss is determined by my state evolution values, right? So here, V is just a random variable with the same distribution as my signal, and it's independent of Z, which is just a standard Gaussian random variable, right? And the mu and the sigma are given by the state evolution. So in particular, right, we can look at some examples to make this concrete. So the first thing is, what if we take, my pseudo Lipschitz function to be something like the following, right? Then what does our theory guarantee, right? Well, it says that the following. So we have 1 over n times ft xt minus v norm. Okay.
This is your measure of accuracy or success or loss, and now you optimize ft to get the best thing?
Yes. Yep. Okay, so that's 2 slides from now. All right, so what we get is if we look at some examples, right? So this guy limits to the following. It's an expectation of ft mu t v plus sigma t ct minus v squared, right? So this is just the result that we got from the theory, right? And then we can sort of show using the state evolution that this is equal to sigma t plus 1 squared minus 2 mu t plus 1 over theta plus 1, right? So in short, something like the mean square error between the estimate that I get from my AMP and the true signal is determined by my state evolution parameters, right? These are just the mu and t from 2 slides ago. The same thing, maybe you're not interested in mean square error, you're instead interested in an overlap sort of metric, right? Well, we can use the same thing. The state evolution says something about the inner product and also about these norms. So this, for example, is going to limit to something like t plus 1 over theta sigma t plus 1, right? Okay. And so,
do you remind us what's sigma t and mu t?
sure. So these are just these guys that are come from the state of, so it's the recursion. Yeah.
So mu t is the signal and sigma t is the noise.
Right. Exactly.
So is it basically saying that when you're analyzing AMP, you could imagine that you're just working in 1 dimension, but you have like fresh noise. The W is like a fresh noise in each iteration, and whatever you get in 1 dimension, the accuracy you get in 1 dimension will be the accuracy you get overall.
Yeah, I think so. There's some heuristic sort of like the proof I gave. There's heuristic proofs that'll motivate things like this, where it's just like if you instead analyze the iteration where with each iteration t you put a new matrix in, then this sort of state evolution will pop out, and you'll see. We get the same thing, and then the argument again is like, okay, well, the role of the Onsager term is to act as if we get a new random matrix with each iteration. And then, yeah, so essentially, right, so basically then, when we look at, where am I going? Other way. Something like this, right, now we just have a one-dimensional kind of thing that we're looking at. So exactly, it's sort of like, even here, right, you can see that like what you want is this to be big compared to this, right? And so then what you try to do is just, since the mu and the sigma depend on the f, can we find an f that optimizes that ratio? Okay.
Can I ask, like, in the previous slide, how you get to the equality? I just didn't quite follow the slide.
Wait, this one?
Yeah. You have.
Right. So, okay. So we get expectation of this term squared, which is the sigma t plus 1 squared, right?
Okay.
So this guy, then you get the 1 comes from expected value v squared, and then the cross term gives you. Okay, right. So, okay, what we've all been waiting for. How do we choose FT, right? Okay. What I suggest to do here, and this extends beyond just like the matrix estimation problem, but essentially you want to choose the FT to minimize or to maximize your signal to noise ratio. So here I'm going to define my signal to noise ratio to just be the ratio of the mu and the sigma, right? Which is kind of motivated for many reasons, right? We can see that, my sort of iterate xt looks like this, right? So we'd like mu to be big relative to sigma. We can also see that, asymptotically, the overlap between my estimate and my truth depends on this ratio. So maximizing this ratio is something we'd like to do.
Is it clear that's exactly what you want? I mean, I see that it goes in the right direction, but if I want actually the optimal recovery, is that the same as optimizing this ratio? If you go back to the previous slide, I mean, if I want to get the best mean squared error, then it's not. Is it exactly that? Wait.
Yeah. So what you actually find is that yes, well, if you maximize this, what you find is that you get the conditional distribution denoiser, and this maximizes both the overlap and the mean square error. And like, even if you care about a metric that's not either of those two, you should essentially still run AMP with this in it, and then, kind of at the end, denoise and denoise in the way you want somehow. So that makes sense. So, okay, in general, when folks run AMP with this sort of conditional distribution denoiser, this is referred to as Bayes AMP. So for various reasons, right, this is called the Bayes denoiser, and Bayes AMP is when AMPs run with this denoiser. So sometimes when people talk about AMP, they're actually thinking about AMP specifically with this denoiser, but you can choose other functions too. So for example, when AMP was originally studied for compressed sensing, sometimes folks would run AMP with like the soft thresholding function here, right? Which might still be something you want to do if you want a sparse solution. But in terms of maximizing signal to noise ratio, this is the right idea. Okay, so I wanted to make the point that, okay, so now if we use optimal denoising, which I just mean so I'm calling the function ft a denoising function, right? So the idea being that, ft in our algorithm takes as input, terms like this, right? So its function should be to denoise them, right? So it's often referred to as a denoising function. And so if we run our AMP algorithm, again, thinking about this rank 1 matrix estimation problem with this denoiser, then it turns out that my state evolution simplifies. So earlier, remember, this is the state evolution we're looking at, but you can kind of see that if these are conditional distribution things, then things become more simple. So what happens is with that specific FT, yeah.
I'm still confused with that. So you're optimizing each mu-t and each FT conditional on the previous FT. Like you're optimizing, it seems like you're optimizing sequentially. Right? Like you're optimizing because they're all dependent on each other, right? I mean, the mu-t's and sigma-t, mu-t and sigma-t depends on mu-t minus 1 and sigma-t minus 1, right? But when you're optimizing it, you're not, like, if I understand correctly how you chose it, you're not looking forward. You're only looking, you're just optimizing it for this step. And then you're optimizing the next step. I tell you, maybe I'm misunderstanding.
Yes, you're optimizing only based on the previous T. Mu-t and sigma-t, and that's how you choose
the next
one.
one.
I mean, that sequence is, well.
Is that optimal actually, or
Which next one is increasing function?
Yeah.
But if I care about, if I know that I only care about what happens in iteration 100, so I want to get the best the gamma 100.
Right.
Is it clear that I should choose the optimal the optimal gamma 1 and optimal gamma 2 and optimal gamma 3?
because monotonicity, yes, because
No,
there is no
it's
reason you want
monotone.
less.
Suppose that you choose all the last ones in the optimal way. Then the first one, you have to choose it. The last one, if they are optimal,
No, but the optimal gamma. Okay, so I guess what's not clear to me is that the gamma, the optimality in gamma, that if I improve gamma, because the dependence was not on gamma, it's on mu, t, and sigma t separately. But you're saying that if I improve gamma 3, then I'm gonna necessarily, if I give you a better mu 3 and sigma 3 that gives a better gamma 3, then you'll be able to do better for gamma 4.
Maybe one way to look at it is the scale. It's scale free, right? If you multiply f by something, all the mu and the sigma, it doesn't matter. So you really only care about the ratio of mu and sigma and not their individual values.
Oh, but okay, I guess I don't see, because it's not just mu and sigma, it's also ft that I did.
I think from state evolution, that what your iterative will always look like some mu times your signal plus some sigma times your noise. And once you know that, it's a good idea to increase mu relative to sigma as much as possible.
So I don't care about the horizon. I can just do it.
you can always absorb one of mu and sigma into f, right? Because f you are optimizing. So you can decide that this is instead of mu b plus sigma z, is gamma b plus z. And sigma is always constant. So now you are very caution in
Okay, fine.
it's a one-dimensional recursion.
Okay,
It's
then
obviously
it's-
monotone increasing.
Okay, so that's sequential. Okay, sorry, thank you.
Okay, so this is kind of what Andrea was saying, right? So when we use the optimal denoiser, what we actually see is that the state evolution simplifies to just a single recursion, right? So now we can think of the state evolution as just a recursion on the signal to noise ratio, right? It takes the following form, right? So we initialize with some gamma naught that's based on our initial correlation with the signal, right? And then we update with respect to some MMSE function that just calculates the Bayes risk with respect to L2 loss based on the previous SNR. And so what one can show is that if we think about the state evolution iterating now in T, the state evolution is going to converge to the smallest strictly positive fixed point, right? So this tells us that if we run the AMP, our performance metrics are going to be determined by the strictly smallest fixed point. And so I bring this up because this is kind of,
Right?
yeah, smallest is worst, right? So, this is our SNR, so we'd like it to be big. So if we have multiple fixed points, what's going to happen is AMP goes to the one that's not as good. And so this is how we kind of tie in these AMP algorithms to the sort of computational limits of problems, right? So to do this, what we want to do is compare this to the information theoretic limit of the problem, right? So if we just, want to think about something like minimizing the L2 distance between, the true signal and some estimator that I have that takes as, that uses my data matrix, right? We know that the way to minimize this mean square error is just by choosing my estimator to be the conditional expectation. Right? And so the performance of this estimator has been analyzed before by, Jean and Lalarge and Mielaine and others. And what they show is that the performance of this Bayes estimator is actually described by sort of the same fixed point equation, right? So it's also described by the fixed point of what we just saw as our state evolution recursion over here, right? So this guy and this guy, sorry, my bad. This should be a gamma, not a. Okay, but what we see for the Bayes estimator is that it's going to attain a fixed point of this equation that's described by some potential function. And so the details of the potential function are not necessary, but we know how it's going to perform based on characteristics of the problem. So what the kind of conclusion is, right, is so if our state evolution has one fixed point, right, then great, AMP attains it, and that fixed point also characterizes the performance of the Bayes estimator, right? So AMP is doing as good as it can, right? Hence, there is no statistical computational gap here. But on the other hand, right, if there are multiple fixed points, like we pointed out, then AMP is going to hit the one that's not as good, right? And so could be subpar in those settings. So I'm going to give an example where it hits something that is not as good as the Bayes risk. Okay, but I just wanted to comment briefly to make this a feasible algorithm. I needed to address the fact that I sort of cheated when I initialized the algorithm. So in the beginning, right, I assumed that my initialization for the AMP algorithm was correlated with my signal V. And so you can kind of see why we need this to be true. So for example, if, so here, this is V, my random variable that's distributed in the same way as my signal. So if my signal has mean zero elements, and instead I initialize with something that's not correlated with V, then what happens? Well, we can see that the signal strength term in my state evolution, my mu1 term, just exactly equals 0, right? And so what's going to happen is, we run the state evolution, but this mu is going to continue to equal 0, right? And so, I mean, that's bad, right? Because, the overlap metric, for example, had that mu in the numerator. So if it's equal to 0, then this is saying the AMP is giving us a result that, isn't correlated with the signal at all. So the AMP, is functionally useless, right? So if we have a mean zero signal, then we need something that correlates with the truth. I'll mention if the mean of the signal is not equal to 0, then you're all good because you can just initialize with like a constant vector or something. But it turns out, that what you can do if you're in this situation where your signal has mean 0, then you can just use your initialization as the principal eigenvector of your data matrix. Okay? And so it turns out that, well, why is this a good idea, right? Well, random matrix theory tells us a lot of things about the principal eigenvector, and in particular in this problem, it tells us that if the signal strength in the problem is large enough, right, then our principal eigenvector is going to be correlated with my true signal at some level. And if the signal strength is not, then my noise just totally washes out the signal and I don't get any correlation. But the idea is, okay, so let's imagine we're in this regime where the principal eigenvector is useful for us, right? Then what we can do is just initialize AMP with this principal eigenvector. And so it turns out that this works in practice, but since now we are not in the setting where my initialization is independent of the matrix that I'm using to run the AMP, the standard theory no longer holds. So the theory that I built up until now assumed independence of the initialization and my matrix, but this is no longer the case here if we initialize with the principal eigenvector. But the happy ending to this story, at least, is that the theory still goes through in the ways you would expect it would due to Ramji and Andrea's recent work.
So should we think of it as if the heavy lifting in some sense is by the principal eigenvector, and then AMP fixes, so it provides a warm start for AMP, and then AMP kind of fixes to get the best estimator from this approximate version? Or should we so I guess the question is, like, you really need a correlation that is independent of n, right? That's to get things going. Is that so you need some vector that has significant correlation with your signal that is independent of n. So that's so basically AMP requires some type of warm start.
Yeah. So I mean, yeah. I mean, I don't think that's necessarily the right way to think about it, right? Because, like I was saying, if just you have like non-zero mean here, then well.
But if it's non-zero, then it is dependent on n, right? So it's like a constant correlation.
Yeah.
Okay.
Yeah.
Here is another way to say this theorem. We run AMP for log n iterations using f, a linear function. What you will be doing is the power method, and will compute basically an approximation of the leading eigenvector. And then I'll change the function to the optimal base function, right? So I'm doing a strange version of AMP, but now you say, still I'm not happy with this version that you're proposing. I want to use the base optimal AMP from the beginning. That we cannot analyze that.
No, I believe it will work. I just want to get like an intuition whether I should think of it as basically a two-step algorithm where the first step you need to get like a warm start and something that has a constant correlation, and then you do this base optimal thing to really nail down the two maximum correlations that you could possibly get given the signal.
But the point is that the base optimal thing at the beginning is a linear function, essentially, because if you have a random variable plus a humongous noise, the base optimal estimator is so all of this is not quite filling all the gaps.
Sorry, just to understand that, is the follow-up result only for it's only for the ±1 uniform prior, right? Like if you have like a sparse prior and stuff, then you would you need significantly higher signal than the SNR for the eigenvalue or for the leading eigenvector to work, right?
Sorry, you're asking just here,
Yeah.
like what?
Right.
Yeah.
But if you don't pass the spectral threshold when the eigenvalue pass out, that is the Statistical threshold, right? So if you don't pass the threshold, that fixed point is stable, and we don't know of any output in the time.
Sure. But I'm just trying to understand that in some sense, the Statistical threshold corresponds to the one which corresponds to getting a good initialization from.
Okay. So right. Okay. So All right, with the spectral initialization, then, like we have a full algorithm to run, right? And so here's like some examples of just, you know, what happens with this, the performance of AMP versus like the Bayes estimator, right? So if we're in this setting, right, where our signal elements are equiprobable 0, 1, or plus minus 1, right? So this is a case where it's mean 0, so we need to use the spectral initialization. Well, in this case, AMP with the spectral initialization has IT information theoretically optimal performance. As another example, right, if we think about an initialization where the values take plus or minus some value A with probabilities epsilon and 1 minus epsilon, so that we remain mean 0 and variance 1, then what we can show is that the state evolution is going to have multiple fixed points, and AMP is going to perform strictly worse than the Bayes optimal estimator. And so there's like a little caveat here, right, that AMP with spectral initialization needs the our signal strength, the theta, to be bigger than 1, and you know, the Bayes optimal could work without, but that's the.
And
Yeah.
for the second problem, you know that is it believed that for that specific problem, it's AMP achieves the algorithmically optimal threshold, or it's so below that it's algorithmically believed not to be probable, or
Some people have made the conjecture.
I think what she calls here plus minus 1 with priority, plus minus alpha with priority epsilon and 0 otherwise. So this is the sparse case, right? So yeah,
Wait, that's.
at least I don't know of any algorithm in all of
right?
these.
And but this, sometimes we don't know algorithm, but sometimes we have a reason to believe that there is no algorithm. So
What do you call the reason?
So question, can you give a sense of how FT looks like for this, and also how different is the optimal thing from the naive thing? Just like the spectral approximation? For both of them, I guess, are mostly different.
Yeah, so if you just take the spectral initialization, there's like an example in the paper. I mean, the MS, like the mean square error of the AMP algorithm is like, you know, strictly below the limiting MSE of, or like the MSE of like the spectral initialization. So the AMPs does better, right? Like if you're saying if you just take.
Yeah, but by
Yeah.
how much? Like how many more samples do I need in order to get the same performance? Like,
Yeah,
is it
I don't.
constant, small constant factor, or is it like?
Yeah,
Like
I'm
if
not.
you're doing AMP and I'm just doing spectral, like how many more samples do I need to reach your performance?
I don't know offhand. I mean, do you have a good feel for how much?
I mean, in this problem, so you know, all the errors are constants, right? So, but you know, you can look at how they go to 0 in SNR. Okay, SNR, this goes down like this first polynomial, yeah, 1 over SNR.
Okay.
The error versus you know, any of these methods goes down like exponentially.
Oh, okay, so it's a huge. No, that's a bit, no, but that means that I would need like I mean, if you're doing AMP and I'm doing spectral, I'm going to need many more samples to get the same.
Right. Okay.
And how does it? No.
Yeah, it's a long story. We can go and dinner together.
All right. So I will, let's see. Okay, I'm gonna mention just 2 generalizations, and then I'll say like 10 minutes on generalized linear models. So the first extension is that, you know, we can extend all of this to a non-symmetric version of AMP. So if your matrix is no longer a GOE matrix, but now you're just an IID Gaussian matrix, there's an AMP for you too, right? So now, since we're not symmetric, we have 2 iterates. They, sort of mirror each other. And the theory kind of looks the same as before. There's not a lot of point to stay on this. You can prove it, directly by considering the two different iterations in the same way you consider the symmetric one, or you can reduce the non-symmetric version to a symmetric version and use the original theory. You can also extend this to matrix iterates. So now, we have our two-step iteration, but now we're thinking about the BT and the HT no longer being vectors, but instead being matrices of fixed size. And, everything kind of goes through like you expect, the derivatives are now Jacobians and these sorts of things. And you can kind of, with some practice, guess the theory and the state evolution and so on. And it turns out that like the AMP with matrix iterates, so this is Javanmard and Montanari analyzed this in the beginning. It's useful. It, for example, is the way to prove the generalized approximate message passing that I'll prove next. So these extensions exist, but they're more or less like as you would expect somehow. Okay, so for the last like 15 minutes, I will just say some words about generalized linear models. So here my idea is, okay, I have some signal that I'll call X now, and let's assume that its IID, its elements are IID according to some distribution. I have some output Y, and now I have a matrix that's IID Gaussian, and this is all connected via some function Q. So the idea, right, is that my output is generated by some conditional distribution here based on the linear measurements of my signal, right? And so if this Q comes from an exponential dispersion family, statisticians call this a generalized linear model. Yeah.
I just wanted to say that you shouldn't rush to try to complete the topic.
Okay.
We started quite late the second half, so you can, you should go until 4:30 or something.
Awesome. Yeah, we'll see what we can get through, and I'll stop when it seems normal. Thanks. Okay, so right, so generalized linear models, right? This is a class that includes like standard linear models. It also includes things like logistic regression and Poisson regression and phase retrieval and so on. Okay, so right, in short, the intuition for the GLMs is kind of like, you can think about it as a two-step process, right? So I produce an output from my input signal X. How do I do that? Well, the first step is I take linear measurements of X through my IID Gaussian matrix A, and then I observe my output based on some conditional distribution of Y given those linear measurements, right? So this just includes, other noise models, for example, than additive Gaussian noise or whatever. All right, so okay, so there's an AMP algorithm to use if you'd like to recover the signal in such models, right? And this is called GAMP or Generalized AMP. And it looks like the following. So you're gonna initialize with some U naught that's independent of my ID matrix A. So for example, I could just take my U naught to be, or my U0 to be a constant value, constant vector rather. And then I update my AMP algorithm in 2 steps. And so this should look a little bit like the non-symmetric AMP we saw 3 slides ago, but the difference is now, this function here with the G, it includes my Y, which is my output value. So this complicates things a little bit, right? Because the Y is, dependent on things like my matrix, right? And so it turns out that for this generalized approximate message passing algorithm that Sandeep Rangan initially studied, it has in fact, a different state evolution than just the non-symmetric AMP, right? So the fact that this y is here in these functions changes the dynamics of the algorithm. I'm not gonna like show you the state evolution because it's kind of complicated, but it's there, right? It's the same idea. It's a deterministic recursion that tells us something about the dynamics of the algorithm itself. So, okay, so what I want to do in the last little bit is, okay, I'm gonna just discuss some of the theory for the generalized approximate message passing. I'm going to link the GAMP algorithm to convex optimization problems, and then give some steps for how to systematically derive exact asymptotic expressions for risk of estimators and GLMs that, you know, when the estimators are solutions to optimization problems. And so, you know, I was going to end with like a nice example about showing properties of the lasso estimator, but I don't think I will. I will just stop after I've given some systematic way to do this. So this is the part of the talk where it's like, how do we use AMP to give us statistical properties of things like the lasso estimator, right? Or, you know, like Pragya studied logistic regression and these sorts of things. Okay. All right, so here's all I'm going to say about the state evolution for the general approximate message passing. It's, in short, you know, what the theory shows is that the iterates of this GAMP have empirical distributions that converge to, sorry, so this should be like converges to the distribution of this, right? Where, you know, importantly, the X in our algorithm, this gives us the estimate of our signal and our GLM. So our, you know, what does it look like? Well, it basically looks like, again, you know, something that's the distribution of the signal itself and independent Gaussian noise. So where the signal strength versus the noise is determined by this state evolution. So now, you know, it's like the state evolution has 4 different values. They're all recursive. It's a little bit complicated, so we won't look at it. Okay, and so in general, right, like all of the same things we discussed before kind of hold true for this generalized approximate message passing algorithm. So, you know, you can choose FT and GT by maximizing SNRs. They give you a sort of condition, it suggests conditional distribution denoisers. You know, the convergence statements can be made about the joint distributions of the iterates. You know, it can also be written in terms of pseudo-Lipschitz functions and so on. And then, you know, there's also theory for the spectral initialization here, which, you know, similar to before when we were looking at, you know, low rank matrix estimation, and if the signal has, or rank 1 matrix estimation, the signal has mean 0, you need some sort of smart initialization. There are settings here where you do need a smart initialization, and Marco and Ramji wrote the theory for this. I'm gonna skip this, I think. Okay, so what I want to do is link the GAMP algorithm that I just showed you to a convex optimization problem. And so the high level idea is, you know, if I have a convex optimization problem in a specific form, then I can choose the FT and the GT in my GAMP algorithm in such a way that the fixed points of the GAMP actually are minimizers of my optimization problem. And so that's kind of the program I'm going to give you in the next few minutes. So the idea is the following. So we want to look at constrained optimization problems like this. And so the motivation is that, you know, for many of the estimators and GLMs, they're, you know, computed from some sort of optimization like this. So we're optimizing a cost function over you know, some signal X that we're constrained to have the correct linear measurements. And the structure of the cost function is that it decouples into a sum over loss functions. So this is like my, you know, y minus AX squared term, and then also penalty functions. So this could be something like an L1 penalty, right? Okay, so the program, right, is if your loss function decomposes into, or sorry, if your cost function decomposes into this form, then we can write a GAMP algorithm such that the fixed points of that GAMP algorithm solve the optimization. Okay. So, right, so I just wanted to give some examples of, cost functions that have this form, and in particular, the MLE and the map estimator both do. So, what is the MLE, right? Well, theta hat MLE, x hat MLE, right? How do you calculate that? Well, it's just going to be the argmin over a sum where, it's the negative log likelihood, right? Where my likelihood now is described by this QI function. Similarly, right, if my signal elements are IID according to some PX, then my maximum posterior estimators are going to optimize this, but then they'll have a term for the priors, right? So it's going to be something like argmin with the constraints on the other slide, I equals 1 to n negative log UI, then plus the sum of j equals 1 to d negative. Yes. So these are, two such estimators that are solved as, optimizers of the cost function with the form that we're interested in. I mean, another one is like the lasso, right? Or whatever. Many of your favorite estimators probably have this form. Okay, so so what we want to do is assume this is a little bit of a sticking point in the analysis, but we assume that J and L, so my loss and my penalty, are convex in their first argument, and if we can make that assumption, then we can design a GAMP algorithm whose fixed points are the solutions. And then how do we use this? Well, then the GAMP theory gives us exact high-dimensional asymptotics for such estimators, so long as we can prove that the algorithm converges to its fixed points. And so that's going to be the strategy that we lay out ahead. So before I introduce the GAMP algorithm that solves the optimization problem, let's just remember what a proximal operator is, right? If we have a convex function M that's a scalar function and some parameter eta, then my proximal operator is also a scalar function that just solves this minimization problem. And it has a lot of nice properties, like it's Lipschitz and non-decreasing. And so this is useful for us because it turns out that if we want to run a GAMP algorithm that solves the convex optimization problem, then what we should do is choose the FT and the GT to be proximal operators. So so this is, so the form of the FT that we need is some sort of proximal operator that acts, with respect to the penalty function. And then the form of the GT that we need is a proximal operator that acts with respect to my loss function there. I maybe won't say much more about that, but the sort of takeaway is if we use these, the form is like, I don't think that informative, but just let's, the sort of what I want you to hear, I guess, is that if we choose the F and G correctly, then what happens? Well, this nice thing happens, which is that if we find a fixed point of the GAMP algorithm, so a fixed point in terms of the U and the X iterates, then that fixed point, evaluated in sort of the fixed point functions as well, solves the optimization problem, right? So it's going to be a minimizer of the optimization. And so, okay, so this is all, like well defined. So, these are Lipschitz by the Boyd result I just showed, right? And since these are convex, now this is the solution of strongly convex, the minimizer of strongly convex thing. So it all checks out. Okay. And so, all right, so to wrap up, right, what I wanted to do is, okay, so if we know this is true, right, then the kind of remaining point is that we need to show that our GAMP algorithm actually converges to this fixed point. And if that's true, right, then what we can kind of do is push the like GAMP theory, these state evolution performance guarantees, onto the minimizer of the cost function, right? So in particular, if that minimizer is like an estimator, like the lasso estimator, then now if we can show that our GAMP algorithm finds that that estimator, then it sort of inherits the state evolution guarantees, right? And so to wrap up, I just wanted to give a quick general strategy for doing this. And so in the paper I mentioned earlier, we lay out this general strategy, and then we show that, the results for the lasso and for M estimator. So the lasso was Beati and Montanari, and the M estimator was Donahoe and Montanari, and correct me if I'm wrong, and the Pragya studied logistic regression with this sort of strategy. And so we show that, all of those sorts of works use the same kind of approach to analyzing characteristics of those estimators. So the strategy is the following. So the first thing you need to do is find a fixed point for the GAMP and for the state evolution. And so usually finding the fixed point of the GAMP just becomes kind of a, like solving a set of linear equations. So it's straightforward. Once you've found the fixed point, you sort of need to consider a stationary GAMP. And so the idea is that the stationary GAMP is initialized via an oracle. So it's initialized, with something that uses the signal that you want to recover. So it's no longer like a feasible algorithm to run in practice, but it's for theoretical purposes, it's nice. And so once you initialize with the oracle, what you can ensure is that the state evolution is stationary. So you kind of initialize the algorithm such that the state evolution starts at its fixed point. And so then as the algorithm iterates, the state evolution remains at its fixed point. So with the stationary algorithm, right, now your GAMP theory says that every estimate BT from the algorithm has the distribution that's given by these state evolution fixed points, right? You initialize in such a way that the state evolution stays the same. And so kind of the hard part of this general strategy is actually showing that the stationary GAMP converges to the fixed point, right? So you have a fixed point of the GAMP, but do we know that the GAMP gets there if we run it? And so what you'd like to do is show that this is true in the sense that something like this happens. So, if we have a fixed point that's x hat, and this x hat t is, the iterate of my GAMP algorithm, then what I want to show is that, in this sort of high dimensional limit, and then as we run the algorithm limit, the mean square error between these two goes to 0. And so once you have this, then, what do you have? Well, your AMP algorithm converges to the fixed point, and we know that the fixed point is the minimizer of the cost function. So now we know some statistical properties of the minimizer of the cost function based on the state evolution. And so it turns out that this is like, proving this is not too hard if your cost function is strongly convex with high probability around the solution and around the AMP iterates. Essentially, you just have to show some sort of Cauchy property in the sense that the iterates of the AMP are getting closer together. And you also have to show that, you know, your cost is approximately minimized by, you know, the output of your AMP. So the way, you know, one could do this is show that, you know, if you have something in the subgradient of your cost evaluated at that point, then the norm of that subgradient is small. And so this is kind of the non-trivial part of the whole thing, especially when, you know, you don't have the strong convexity assumption. So if you have strong convexity, then you're more or less done here. But if you don't, then there's some extra work to show that it's unlikely that this subgradient is small and, you know, that this guy remains large. And so that's usually the subtle argument in most of these cases. And so I don't know, I was gonna end by going through you know, these steps for the lasso problem, but that's probably gonna take me a while. So I'll stop here, but you know, if anybody's interested, I'm happy to like go through the steps at some other point, you know, just catch me like in the coffee room or something. So I will stop here. Thanks so much for your attention.
Right, thanks so much, Cindy, for a really, really excellent tutorial. I guess we'll take questions now.
For the convergence to the fixed point, can we also show like a stronger property? Because like if we want to use AMP performance as the computational frontier, we would want like, you know, with polynomially many iterations, like to recover the signal. In the convergence, you showed the asymptotic one. Like, can we show a stronger one? Like, you know, it converges in like polynomially many steps.
Yeah, so I think, I mean, so.
One of the limits was that
Yeah.
the D goes to infinity,
Yeah.
infinity of T, right? Right.
Yeah, so you have to have this going first, right?
So that means that it's all at once.
Yeah.
How crucial is the Gaussian? Can you go beyond Gaussian here? Because I mean, at least the what you worked out carefully, it seemed like really rest heavily on the rotation invariant.
Yeah.
So
Yeah, so I mean, so I mentioned briefly that there's been some works extending beyond the Gaussian. So, you know, if the matrix A is not Gaussian, but instead it's right rotationally invariant or something,
yeah,
it can go through, but
yeah,
you still
but
need
they're
the
going-
rotational
right, they're
invariance,
going
right?
on, but it's not rotation invariant.
Yeah, so they can extend to like IID sub-Gaussian, but you know, like it's in practice, the AMP algorithms work, for example, if it's like a Fourier transform matrix or something, so, or often work. So they seem to, in practice, work more widely than what we've proved here. And I think like to extend the theory, you might have to, you know, have a different proof technique than what I showed, because like you're saying, it's really like rotationally invariant. You know, it's important that that property is there. So.
Also, I mean, the generalized linear model, which you didn't show the details, I guess also the rotational invariant is crucial there also. So I need the data to be.
Yeah.
But for instance, you can do IAK Gaussian rows with
So that we're each So the covariance of the covariance of the covariates does not have to be spherical. You're saying.
Yeah, you can push that in the update equation. You can widen the covariance and that.
And you get still the tight answer, or you only something up to the condition number or something.
So now the tight answer becomes more and more complicated.
Yeah. But you still have to know the covariance structure.
Well, but this is for the analysis. You don't need it for the output, right?
Yeah, I guess.
Oh, but to select the FT, you don't need the optimal F.
Decided.
Yeah, I think you.
Yeah, probably was.
Yeah, you need to know something because you need your FT to, I think, do the blindness.
Finite rank plus noise, but for FT you need the knowledge. But the number of equations, like the state evolution, that's like how many equations, that's
Where I couldn't.
so like in the state evolution characterization, like how many equations sort of go in there? Like what are the parameters? That's gonna, the covariance structure is gonna come in there. So you might have more equations. It's gonna depend.
Things like balloon to get like nasty enough that you won't show them on a slide pretty quickly. And how you start generalizing. So.
But in some sense also like the philosophy of AMP, if I understand correctly, is that you're trying to eventually kind of reduce everything to a one-dimensional problem. So you kind of need some type of symmetry for this, even if not full spherical symmetry.
But again, if you do, for instance, the lasso with IAD Gaussian variance, you still have a two-dimensional problem. Sigma is bounded away from zero. You can do it various ways. You can mix it with AMP. The point is that this fixed point equation, now this fixed point equation, instead of having the expectation with respect to a Z, a Gaussian distribution, it becomes expectation in the V dimensions. Right? So now this becomes very complicated. Now, at a certain point, you're right, the utility of this is diminishing. So yeah, you have to find a way to.
But sort of, it seems that if they have like, I don't know, like sparse covariates or like some hierarchically structured covariates, then this seems, is it correct that this would not be the right tool, or is there still hope of, I mean, like things that are really not rotation invariant and no, so are there papers that look at the AMP type methods
not
for
with AMP, but there are papers that look at.
Right.
Yeah, so I mean, there's a parallel approach which uses Gaussian comparison inequalities, but the framework is similar as in the D by N going to constant. It's sort of a parallel approach gives similar results usually. So in that case, for some problems, you can extend to the finite rank plus noise.
But you can extend to one by you can write the equation for any sigma.
Oh, you can write it for any sigma, but then sort of if you want like very tractable equations,
Right.
scalar equations, then there are some cases where it's explicitly worked out, but even without that, doing a sigma to the half kind of multiplication, you can write that.
Well, like you can write out the equations and then the theory follows from like the non-separable.
Right.
Right, so you can write that out.
Yeah.
We saw that AMP finds a fixed point of this NLSC equation. Do we know any other ways of finding this fixed point?
So the question is like, is there any other algorithm that performs as well as AMP for doing like the lower rank matrix estimation problem?
Yeah, that's cheap.
I don't know. Anybody in the room have a suggestion? No, I don't.
Right, the only thing that we can also be try to do something like Inference the local analysis. I don't know. must be, actually, it's an interesting how to do a version of that's
Generally, you could imagine sparsifying, right? So just subsample.
but you get nothing because this is that, right? So if you sparsify, you get. Yeah, each entry has mean 1 over n.
Oh,
Your
okay.
matrix, and the variance is, I mean, standard deviation is 1 over square root of n, right? So each single entry is contained.
You cannot do like a spectral spacifier or something like that. Find like a sparse matrix that approximates this matrix, and then you do everything with that. That won't work.
Fantastic, so let's think Cynthia.